Josh will give his second talk.
Perfect. Excellent. Yes, thank you, Chris. Thank you all for coming for day 2.
Josh, since you started, you may just go another time.
Yeah. Actually, so, maybe I shouldn't say this. I'm not planning to do the whole hour. We'll see how it goes. But, yeah. Thank you. I'll take it if I need it. Good. I want to talk about a toolkit for isomorphism. So last time I was talking about tensor isomorphism. Okay, and it looked something along these lines, and this is also a bit of a refresher of the notation that I'm using. So I had V1 all the way up to VL, that's an L, and V0, and I might call this S, and then I have another V1 up to VL, and I might call that T, for example, right? And isomorphisms. Of course, we saw many examples of different kinds of isomorphisms in different categories or context, if you like. The one I'm going to consider and continue considering is the one that requires you to come up with L+1 isomorphisms, and they can, of course, be distinct. Okay, so that is tensor isomorphism from last time, and we're going to now look a little bit at a few tensor isomorphism invariants. Okay, so this is all about tensor isomorphism invariants. Mostly. It's not at all exhaustive. They would just, I couldn't do that in 1 hour by any means. So I'm going to just pick a few. Of course, there's many more, and I think many other people are talking about some other ones as well. So, yeah, there's my little disclaimer. What is useful with these isomorphism invariants is they often give one a reason for non-isomorphism. So if I have two tensors, and they have two different isomorphism invariants, now I have a reason why those two wouldn't be isomorphic. Okay? That's what I mean by isomorphism invariants. Okay. The first I want to consider is closely related to the last talk, determinantal hypersurfaces. Okay, so I'm going to consider for this talk, at least this portion of the talk, I think later I'll generalize a little bit more, we're going to want square matrices. Square matrices of linear forms, okay? Mulfs, okay? These are going to come from bilinear maps, of course. Or B, that's some notation. I'm slightly changing the notation from this general style to something like this, okay? So if I have a bilinear map of this form, then I will get square mulfs from this, okay? And oftentimes, and we've seen this many times already, is you have some extra geometric conditions like symmetry, anti-symmetry, or alternating bilinear maps, Hermitian if you like. I'm not going to make these explicit, but they're often in the background here. Okay? Yes, last time we saw how to take a bilinear map, turn it into a multi-way array. So it was just I'm not going to go and rehash everything, but we could go from bilinear maps to multi-way array. And of course, these are equivalent to mulfs. Okay. And of course, we have to actually, I accidentally drew the arrow as a double arrow, but you actually have to choose bases, and then you get your multi-way array. Okay, and this is the isomorphism thing. Okay, good. So if we have a matrix of linear forms, right? So it's a square matrix of linear form. We can take the determinant, okay? And that's what I want to define here. So let's suppose let M be a matrix of linear forms. Okay. Sometimes I go back and forth between multi-way array and multilinear form matrix of linear forms, and of course that's not too big of a deal. Okay. So the determinantal hypersurface is the following. So I'll write it with the V sub m, and I'll try to use a slightly different font than my V's for my frame, the axes, the vector spaces here. So Vn is going to be the hypersurface. The hypersurface in the projective space of W. If you like, just very quickly, take the vectors inside of W. Consider two vectors equivalent. Sorry, the non-zero vectors in W. Consider two vectors equivalent if they're scalar multiples of one another. Okay, that's what I mean by projective space of W. Is the hypersurface in here defined by the equation det m equals 0. Okay, so Vm is my determinantal hypersurface inside of some projective space W. And let's just quick sanity check. If I write a matrix of linear forms, the number of variables is equal to the dimension of W here. K is in the background. K is my field. I haven't mentioned that yet. These are K bilinear maps. So we have dimension W variables here, and we're really looking at that projective space. Yes, okay. So sometimes this is also written as projective space over K. Dim W, you have to shift by one, shift down by one. Okay. So you write that. Okay. So that's our determinantal hypersurface, and I actually want to mention one quick thing. If we assume alternating, then we'll just take this to be the Pfaffian hypersurface. We'll take this to be the Pfaffian hypersurface. Okay. What more do I want to say? Did we see the definition? So when it's an alternating matrix, determinant is a square. That square root is the Pfaffian. Okay. Oh, and in this context, this is important, and this word will come up in other talks of mine. In this context, isomorphism is a bit special. So here we have the same vector space, and so I can operate on the same using the same matrix. I can have a matrix X acting on this vector space, and I want to use that on this one as well. So isomorphism is actually I'll just write it like this. How about that? W is, I will have some matrix X, but let's just use matrices. So matrix X, that same matrix X, and then a potentially different matrix, well, generally different matrix Y. Okay? This is what I mean by isomorphism, and I'll actually give it a special name, call it pseudo-isometry. I think Pete might talk about isometry at some point.
Yeah, I think Friday possibly.
Friday, okay,
Which
cool.
is tomorrow.
Which is tomorrow, as I'm told. Yeah. So you'll see a little bit why maybe this is called pseudo-isometry, but that's just a name to just clarify what I mean by isomorphism in this particular context. Okay? Right. So we have this hypersurface, and we have this hypersurface which is, of course, associated to M, a matrix of linear forms. But if we back up and we go to B, we know that there's going to be a problem. In general, VM is not canonical in the sense, it's not canonically, how do I want to say this? There's a choice. This involves the choice of bases. Yeah, for V and for W, right? So one could get for a particular bilinear map many different hypersurfaces, VM. Okay, so we've seen last time that the choices of bases can cause issues. We are going to kind of ignore that. So we ignore, and we'll just write VB. Okay, that is not really well defined. Okay, but what can we say about VB?
Could we just repair this by letting VM be like W dual or something, and then I think everything is just
You still need to. No, you get potentially different equations there, I would imagine.
really.
You could change the basis of V, for example. Oh no, you're right. Actually, yeah, you could do that. Yeah, sorry. By changing the basis in V, you just scale. And that's not going to be an issue. Yeah, you could do that too. Indeed. But I'm not going to go and bother with doing that sort of a thing. We can just ignore that, and we'll just talk about the hypersurface associated with B. Okay. Here are some exercises. So construct two non-isomorphic tensors preferably W has dimension larger than 1, with distinct, these should be somewhat large, but not too large, with distinct hypersurfaces. Okay, there's it there. That's a fun exercise. The next exercise. How, let's see, given isomorphic tensors B and B prime, going from B cross B into W, how are the two hypersurfaces related? How are this and this related? Okay. And what else do I want to say about that? Oh no, I actually don't want to make it so open-ended. I actually want to make it not open-ended at all. Not how, well, okay, I'll just leave that there, but I'll tell you the answer, and then the fun is just quickly showing this. They are related by a linear isomorphism. Okay, and that's perhaps not hard to show. Erasing. Should I use this?
You were allowed to.
Allowed to, all right. All right, here we go. Excellent. Okay, linear is pretty restrictive. I could use any sort of polynomial map. But I only want linear ones. Okay. Oh, this has it.
The other
Is there
one
a difference?
works better, that's why I brought it in.
This one's good?
The other one works, to my hand, it works better, but
Good.
you two and you like.
But it's really not the specific hypersurface, generally speaking, that one would use for non-isomorphism. Yeah, showing that two things aren't isomorphic. You might consider features of this hypersurface. Okay, let me say a bit about that. So which features of this would be invariant regardless of what choice of basis, or if you like, use the dual for W there. Which features of this can we easily use to show non-isomorphism? Okay, I'll list a few. They're not exhaustive. For example, you could look at dimensions of varieties. So that. If K is a finite field, you could talk about the K rational points, the number of K rational points, as in those are the solutions to, conveniently erased, to determinant equals 0, determinant of M equals 0. The number of singular points, again, number of points, so I'm assuming finite fields there for those. Splitting field, the splitting behavior, sorry. Splitting behavior of the polynomial det M. These sorts of things, okay? Those are totally up for grabs and are rather useful invariants for showing two particular bilinear maps, two tensors, are non-isomorphic. Just an open-ended question, what else would you consider? Those can get you pretty far, but those are just, only 4 of perhaps an infinite list. And of course, what we can do is we can generalize this further. I was talking about hypersurfaces because it's a bit easier, but you could then, of course, look at minors. So you could consider all minors. Consider the set. I'll just say the set of all I by I minors for I in 1, 2. I haven't given a dimension for V, so I'll just say dim V. Okay. Something like that. Okay. For I equals 1, it's perhaps a bit boring, but nevertheless, you could do all of this for that, and of course, these ideas all apply. So this is one particular isomorphism invariant. And one particular isomorphism invariant that gives quite a bit. You can use a bunch of geometric features coming from this hypersurface or just in general these varieties, these determinantal varieties. Okay. I have another exercise I want to mention. It's the following. So last time we were talking about the centroid, talking about field extensions and these sorts of things. Okay. Let's go back to that in this particular exercise. It's somewhat related to this exercise over here, but now you have a centroid. So suppose B prime are bilinear maps. The centroids, their centroids are isomorphic to a field extension L over K proper, and because we're dealing with finite dimensional vector spaces, this is a finite field extension. Let M and M prime be the multi-way arrays associated to B and B prime. Just choose some bases so that we get something like that. How are these two hypersurfaces related? And these are L hypersurfaces. So they're over the field L, not over K. Oh, whoops. Surfaces. How are they related if, I'll just do it like that. Very good. So we're looking at K isomorphic. Oh, I didn't say that. These two are isomorphic, K bilinear maps. Right, their centroids are extension L over some K over K. They're the same. Let's just identify the two. Now you have two L hypersurfaces. So hypersurfaces over with coefficients in L.
Josh,
How are these
help me
two
catch up with you. What are your assumptions? Your assumptions are that B and B prime are
Isomorphic.
isomorphic. Or are you making an additional?
Yeah, sorry, I forgot to write that.
Uh-huh. And what does that mean?
Isomorphic.
Over K.
Over K.
Over K. Good.
Other questions? Okay. So those are hypersurfaces. Those are the determinantal hypersurfaces there. Good. I want to go now to a totally different set of variants.
Just a quick
Yeah.
question. So the only difference between the last exercise and the exercise 2 that you are about to erase,
Yep.
so the only difference is now we're talking about L.
Yep.
Is that okay?
Yep. You've totally changed the polynomial. You've changed you're looking at Pete's example from yesterday, where he took a tensor over some k, 8191, f 8191, and extended it by a quadratic extension. And yeah, those define two different polynomials. The determinants are totally different. And if you know that the two bilinear maps of B and B prime are K isomorphic, how are these two related? And it's not as simple as there's a linear isomorphism. In fact, in general, there is not a linear isomorphism. I'll just say it that way. The answer is perhaps not too surprising. Okay. Did that answer your question?
Yeah, thank you.
Cool. Okay. Next set. Transversal toolkit. Okay. So, I originally was calling this the transversal pocket knife because as a young boy, my dad let me use his Swiss Army red pocket knife that I just loved to use when we went camping. And so, that's a sign of affection for this set of tools. Anyways, transverse, why am I throwing this word in there? This is not too important really, but it's transverse is describes how operators are acting. Operators are acting on tensors. Okay. There's multiple ways. It's sort of baked in, and I don't care to tease it out from others. You can talk to me afterwards if you like, but I just want to emphasize the transversal here without teasing it out too much. Okay, notational upgrade. James has already actually mentioned this, but it'll be good to just reinforce this. Okay, so you recall that I was writing things in this perhaps very bizarre notation. Yeah, something like this. And now I'm always going to use subscripts, okay? So I'm not going to, well, I'm going to say I'm not going to do it, but I might sometimes avoid it. But I won't do anything like this. I want to always associate to each entry that subscript, and that subscript will tell you the vector space in which it's coming from. This is sort of the tail end of what James was talking about yesterday. And I imagine he's building upon it today, but there we are. So VI is always in VI, and I'm going to always keep that subscript there. We can take subsets. Subsets A inside of what I write is a bracket L. This is by definition, this is just the definition, 1 up to L. Okay, we can take subsets here, and I'm going to say, let's fix the subset A, and B is going to be a complement, which is nothing more than the set L, take away A. Okay, so in some sense, this A and B is a partition of 1 to L. And I might write something like this. To emphasize, I'll use slightly different symbols. U and B. Okay, and what this is just a way of, well, something like this. UA1 up to UA, I don't know, K, if A is size K, VB1 up to VB K, let's just choose J, if B is of size J, that sort of thing, okay? Unwrapping this, and because I'm always going to carry around these subscripts, order doesn't really matter, right? I can write something like U1, U2, and I want to take that as being the same as U2, U1, okay? Now, again, this is not positional arguments. These arguments are now, you know, using those subscripts there. And I'm going to write those subscripts every time, or I'm going to do something a bit more convenient and use a set to help me out. And in the case where, special case, where A is a singleton, I will go ahead and write the following sort of thing to rewrite that. U sub A, and then V sub A bar. Okay, bar would be the same as complement, but putting a C in here is perhaps a bit too small. Okay, so I'll use bar. I don't know. Whatever. Bars. Okay. Anything else I want to say about notation? Is that notation making sense? For now? Okay. Good.
We're always contracting individually in each of the VIs.
Indeed. Yeah, that's right. Good. So at some point, I wrote down a definition of a centroid. I want to use this notation to now write down this definition of a centroid.
George, what's the difference between A bar and AC?
Nothing.
Why?
Because I wrote mostly A bars everywhere, except for right here I wrote AC in my notes. And so I changed things. Sorry. And I will also, one more thing, I will also take the following. If A is a set of matrices x1 to xl, and A is still a subset, I'll do the following. XA, VA, VA bar. Okay? This would mean that the X sub, entries of A are acting on the V sub entries of A, and the ones that are not entries of A do not have those matrices X. I'll write out a few terms, something like XA1, VA1, XAK, VAK, and then the rest are not. I'll just put the A bar down here. Okay, something like that. Good. Yeah, so now what I want to do is rewrite the definition of the centroid, just because we've seen it before, and use it in this style of notation. We can see what, sort of make sure we're, sort of a sanity check, seeing if we're understanding what I'm writing. Say this side of things is more algebraic than the previous. What I want to develop is a bunch of, a general way, pocket knife if you will, to come up with a bunch of different algebras that act transversely, whatever that might mean on tensors. Okay, cent is now, using this notation, x, x1, x0, not just 1. Right, and these are in the endomorphisms. Vi, 0 to L. Okay, and now, right, this is as follows. Okay, and of course this is running over all VIs in the V, in the capital VIs. Okay, this is a sort of more compact way to write down that centroid, but it's exactly the same thing I wrote. Well, I hope it's the exact same thing I wrote. I meant to write this yesterday if I didn't. Okay, so how do I want to say this? There's a lot of kind of notational things here, and I'm even still abbreviating. I still have a for all, little vi and vi, right? There's quite a bit of notation here. What is the essence of the centroid? Well, it's really this equation right here. Well, I should say these equations, right? Because this is true for all I. So here's what I'd like you to remember about the centroid, actually, is you have your centroid for some tensor t, and I would like you to relate this to a particular set of polynomials. I'm not going to use capitals, but I'll use lowercase. These are my variables. X naught minus x sub I, and I want to do this for all I. So for all I in L. That's what I want you to think of the centroid as. Well, I don't care that it's just a set. Actually, I want you to think of it the entire ideal. So this is what I mean by ideal, generated by these polynomials here. And then this is, of course, an algebra, K algebra. Okay, a bit more than that, but K algebra at least. Okay, and this is the start of this toolkit. So one side we have algebras, general operators. On the other side we have ideals. Well, what are we talking about? We're talking about tensors. I want to throw tensors in real quick. What about tensors? Well, I'm going to use the letter N for tensor. N for tensor. The N.
I don't think I understand your notation here.
Yeah.
The xi's live in different spaces here. It seems like.
Xi's. This is lowercase, so this is an element of K, the polynomial ring. Sorry, it's a bit of an uppercase, lowercase battle here. XL. Yeah. So
We're
those.
just writing down this ideal.
Indeed. Yeah.
It doesn't depend on the tensor at this point.
Correct. This is totally independent of the tensor. This depends on that tensor T, but I want you to think of centroid. So if you'll, this doesn't really make any sense, but I'd actually like you to think of centroid as, and this ideal as sort of being coupled together. Because really, where does T come in? T comes in so that I can just evaluate these tensors. But the essence of the centroid is really this defining equation that I boxed in green.
So you think of a functor centroid, T maps to center. T
If you like that, do that. Indeed. Where are the tensors in all this? I'll write it like this for now, but later we'll write something a little bit better. I want all the tensors S, V1, VL, V0, such that the centroid of T is contained inside the centroid of S. Okay, so I'm running through all the tensors of this form, V1 through VL, going into V0. So this subset would actually make sense because the centroid is a subalgebra subset. Let's just not worry about the algebra part. Is a subset of the endomorphism algebra of all the VIs, so that they have the same set of vector spaces. So this would make sense. Okay, this is what I'll write for N. But really, I actually want to take a step back. So I've already, in some sense, introduced the three players. I've got operators over here. I have ideals over here, and I've got, let me at the moment just say sets of tensors over here. Sets of tensors. Okay. Now I want to take a step back. The centroid has actually nothing to do with these three things. The centroid was my foot in the door. Okay. So a step back. And let's do this a bit more generally, and this might help actually address one of Austin's questions earlier. Okay, so a little more, just a bit more notation, just have some symbols there. T is the vector space, the K vector space. I'm going to emphasize K there. Of all tensors of the form V1, VL to V0. Okay, all those tensors. My little x sub i's are my variables, and then this is, of course, my polynomial ring. It's my polynomial ring, the usual thing. And this product of endomorphisms, I don't want to keep writing it. I'm going to use omega. All right, I'm going to think of those as operators, omega. Okay, so that's, I think that's what I want. Yeah, indeed. And now, I'm going to do another notational upgrade here. This is quite effective. James, do you do this in your lectures? Use this thing?
No, I just make the students come up.
Okay, yet another notational upgrade. Now I want to take this rocket and I want to shove polynomials in there. Okay, so let's do it step by step. So let's suppose if, should I use my notation or else I'll screw things up. So M is just a monomial. I'll write it like this if you like. Alpha. I'm underlining just to emphasize this is in multiple variables. So it's some monomial in my polynomial ring. Okay. I'm going to write the following. T is just some tensor, and V is just some collection of vectors in my various vector spaces. Oh, I need one more thing. And omega, little omega, is in big omega, right? It's a tuple. It's a tuple of n plus 1 endomorphisms in the various vector spaces here. I'm going to write it like this. Okay, this is just notation. What does that mean? I'm going to emphasize this in lowercase, not notationally. What is this? Take omega naught, multiply, take the alpha. Oh, and I should say this is in a polynomial ring, so these alphas are non-negative. Okay, I'm not in the Laurent ring, so non-negative. So omega to the alpha naught of t to the omega I, alpha I, vi. Okay, and this is, I'm just doing the notation here, so I'm doing this for all of the i's. Okay, so that's applying to all of them. Omega 1, alpha 1 of v1, omega 2, alpha 2, v2, all the way to L. Okay? Okay.
So V is an element of capital T, and omega is an element of
No,
capital
no,
omega.
okay, so vi is an element of I, and this is of course then for all I in L. T is an element of T. Yeah. Okay, I wanted polynomials, not monomials, so how do we extend this? Did I hear something? No, okay. We'll extend this. Let M1 and M2, and k to the x, be monomials. Okay, I'll show you how to extend it. It's trivial. I'll use the same symbols here, otherwise. You can take, of course, scalars if you like. I'm not putting the scalars in. Whether you consider that as part of the monomial or not, I don't really care. T M1 omega V plus T M2 omega V. Whew. Okay, and what is often useful is really these V's aren't really that important. Actually, I can define an entirely new tensor. A new tensor, T. Now I'll use a polynomial, f of omega, where f is in my polynomial ring. Okay, so this defines a new tensor. How do you evaluate this tensor? Well, you evaluate it using the recipe I've just described. Okay, of course, polynomials, finite sums of monomials, so that's no problem there. Questions? Okay, so 3 sets emerge now. Just going to call them sets. Fix the following. S is a subset T. J a subset of K of my polynomial ring, and delta a subset of omega. Okay? I'm going to define 3 sets for you. And I'm going to, yeah, I'll just write it. J delta, and this n should remind you of this. I'll have an I, S delta, and then I'm going to have a Z. The Z is perhaps the new symbol, but it's on the board. Okay, yeah, right. So what is this? This is going to run through all little t in T. This is going to run through all f in Kx. And this is going to run through all omega in capital Omega. Okay? And what is the condition? I'm going to write it uniformly first, and then I'll perhaps put quantifiers in there if, because that'll probably help. Okay, now let me add the quantifiers. But the missing pieces, so to speak, are for alls. So I fixed the t here, so this is for all f in J, and for all omega in delta. That's for this one right here. F is fixed here, so I want all t in S, and I want all omega in delta. And the final one, omega is fixed for all t in S, for all f in J. Okay? There are 3 sides of the same coin, so to speak.
The European coin.
And I'm just erasing the example, but well, that's fine. So. Okay, and I think this is a easier way to keep track of many different kinds of algebras that act on tensors in particular, like the centroid and other things that are going to come up later throughout this week and next week. Okay? I have very little, and I want to say as well, but I'm also running out of time. So I have a bunch of exercises actually that I want to mention.
You did start late, so if you want to write it down.
Thanks, James. Thanks. Did we talk about adjoint algebras yet? We have defined adjoint algebras? I don't think we have. Yeah.
Did we?
No, I don't think we have.
I was about to.
You're about to. Okay. I'm going to define adjoint algebras by not defining adjoint algebras in the way that Pete will probably define them. I'll tell you a different definition. The adjoint algebra is not exactly one of these, but I'll write something that's technically incorrect, and then I'll tell you how to fix it. I assume that these are all sets here. S, J, delta, they're all sets. If any of them are singletons, I'm not going to write just the singleton set. I'll just write the actual element of that singleton. Just a bit, save some braces. Okay? So the adjoint algebra of T is, well, we're going to do first T. So that'll be in place of S over there. And then I'll take the ideal generated by, if you like, or just a polynomial. How about that? X1. Let me be very specific here now what I'm talking about. V1, V2 into V0. Okay? This is just a bit easier here, just to talk about this way. The adjoint algebra is essentially this. It's essentially this. This is a subset, remember, of the product at the end, VI's, 0 to 2 in this case. Okay, the adjoint algebra isn't generally written like this. You have to restrict. So you sort of map this into, or take the restriction into here, and to make it an actual algebra, you have to now opt something. I'll opt that one. Okay, so you map it into here. It's not changing the underlying set when I take the opposite ring. It's just changing the order of multiplication. So it's doing it backwards, so to speak. Okay. So the adjoint algebra is one of these. We've seen the centroid already, but just because it doesn't hurt to see it again, the centroid of T, and now I'm going to go back to the general V1, VL, V0 is T, and then I'm going to take the collection of polynomials xi minus x0 minus xi for I 1 to L. Okay, that's the centroid. And I want to define some more things.
Josh, before you do this, can you help me understand map this into something? So how do I map this? Is this essentially a projection? Or
Yeah.
just set this to 0? Or what? How do I map this?
Projection.
But then I change the order and I opt.
Projection of sets. Do you have this direct product of 3 sets?
And there's some reason that you interchange the order as well.
Yeah, I want to interchange the order to make this an algebra. If I don't have that, then I don't have an algebra, and I just get the same set.
So mapping as in projecting onto the last 2 factors.
Indeed.
Yeah?
Or you could just say you make a different product on the same set.
Or you make a different product in the same set. Sure.
So you don't
Yeah.
have to actually change the set at all. You
Yeah,
just make it more
yeah.
complicated.
Do that, and then the product is defined differently. Yep. Okay. The automorphisms of T. These are the isomorphisms that preserve T. Is nothing more. I'll write it as aught T. Is nothing more than Z T of the particular polynomial x0 minus the product of these. Okay. The principal ideal that generates is also known as a toric ideal. That's quite nice. What other things do I want to say? Ah, yes, the derivation algebra. That's what I want to say. So the derivation algebra is another one of these algebras. And this is what I'm going to talk a lot about tomorrow, the derivation algebra and the adjoint algebra. And it'll be good that Pete defines it in a different way today, as I assume he will. I see no reason for you to use these Z sets. The derivation algebra of T is, I'll write it with a Z set, and then I'll bring it back down to earth, so to speak, with bilinear maps. Okay. So what is the set of polynomials? It's still just a single polynomial. It's going to be x1 all the way up to xl, and I'm going to subtract off x0. That's the derivation algebra, and that's how I want you to think about the derivation algebra, as sort of an algebra that's kind of associated to this polynomial here. Okay. Now, let me do it for bilinear maps. So it's not so, we've gone up to the 14ers in notation. Now let's come back down to Fort Collins and see how this makes sense. So for bilinear maps T, and I want this to be V1, V2 into V0. The derivation algebra, often written der T, is nothing more than a collection of matrices, if you like, capital X, capital Y, capital Z, sorry for the collision there, but so it is. And these, I'm not going to write it, but these are, X is going to be a matrix, sort of an endomorphism of V1, Y an endomorphism of V2, Z of V0. Okay? That satisfies the following. Tx V1, V2, plus T V1, comma, Y, V2, equals Z T V1 V2. Okay, why is it called a derivation algebra? This sort of looks like the product rule, if you like, on derivatives. Okay, what's my time like? Good, excellent. Yes, now I want to list a whole bunch of, well, as many as I can get through, I guess, in the next 5 minutes.
Can I ask for the automorphisms, isn't it really like the closure of the automorphisms and the product of the ends? Or,
I don't know what you mean by that.
well, to get automorphisms, don't we need to intersect with like GL, VI, and H factor as, versus the
Oh yeah, of course, yeah, you're completely right, I totally forgot about this. Yes, of course, I only want the invertible elements in that set. Absolutely right, yep. That's right. Because you'll get the 0 endomorphism coming in there. And I certainly don't want that, thank you.
But that's an interesting set there. I mean, like, it probably contains the closure of the automorphisms and maybe some other stuff. Who knows?
I share your interest.
It's the endomorphism model.
Huh?
It's the endomorphism model.
What I wrote is the endomorphism model, and I want the
Yeah,
invertible
the
elements of that
invertible
model.
elements,
No, that's not the
That's really it.
Yeah.
I'm not sure that the automorphisms are connected, so I'm not sure you can just include it. But maybe over T, Mark, tell us the answer. He doesn't know. So it's unknowable.
Such authority. Yes, thanks, Austin. I want the product of GLs. I'll just write it like this for now. Yeah. Thanks. Exercises, yes, good. What exercises do I want to write? So many. This one's a fun one. So show that if J, an ideal, generated by homogeneous linear polynomials, then for all S, T not empty, ZSJ is a K-vector space. What else do I want to say? Yes. Another exercise, if you like. Take a monomial M. I want you to consider the Z of S, and S is still the same, so you know that S. 1 minus M. Look at those operators. They're closed under composition, or closed under the composition in omega. And then here I have conclude the invertible elements form a group. Okay, a bit going on there. Yeah, and then you can even conclude more things than just that. Another I want to also mention. Maybe this one you might do first after this or something. I don't know. Think of these all at the same time. If J is an ideal generated by homogeneous linear binomials, okay, quite restrictive, fine. Then this is an associative subalgebra of omega. Under the product that is sort of natural in omega, just composition. Okay, I don't think you wouldn't need to op. Is that right? You might need to op. You're going to need to op. You're going to need to op the right rings, and I'll leave that for you to to uncover. And now it's 11 o'clock. I have more exercises. If you want more exercises, you come talk to me. But I'll stop here. Thanks so much.
So, let's take a few questions or comments.
Or not. Okay.
How do you find these polynomials in exercise to like define automorphisms, derivation algebras, and other things?
That came out too quick, or maybe I didn't hear everything. Can you say that one more time?
Oh, so when you define, for example, the automorphisms or the derivation algebras, there are some like polynomials in exercise.
Yeah.
How do you normally find these polynomials?
What's the, it isn't different wording of the same question, what's the motivation for these particular polynomials, for those algebras? It kind of comes from bilinear maps. Well, okay, so for automorphisms here, you write down what it means to be an automorphism, and just after thinking about it for a little bit, you see that this is the polynomial that one would associate in the same way that we did with the centroid, which is over here. So the automorphisms will have that kind of a polynomial associated with them. Okay, so derivations of t, sometimes this goes under the name generalized derivations, I believe. This is the bilinear case, but I don't know, this is basically just the definition of what generalized derivations are, and it's just a matter of just reinterpreting definitions.
Well, there's more you could say, right? You could say that you could prove that if it's going to be closed under composition, then it has to be a binomial. And you could prove that that the derivations are universal for any linear ones.
Yeah, I haven't gotten to that sort of a thing.
Okay, so there is more reasons.
There are more reasons, indeed, but for what I've just talked about, indeed.
Further questions or comments?
When you say binomial, do you mean a monomial minus a monomial? It has to be this kind of binomial.
Need not be minus exactly. I mean, you're allowed scalars and these sorts of things.
If we have plus, then that means we're saying this thing equals minus this thing. If we compose them, then we're going to miss the sign of the. So
Yeah, but you
Ah.
can use the composition and put the minus sign in the composition. You can just declare a composition where the minus sign goes there.
you're saying we can define a new. We need to define a new product here. It's not the product from.
Yeah, you can do
Yeah, you'd have to define a new product. So what I said, okay, as it was written, it should be a monomial minus a monomial to make it a subalgebra of omega. But if you allow yourselves binomials, and because you'll need to opt things, you need to opt some things. What I wrote was slightly too quick. But if you consider just this set, you'll see that it forms an associative algebra, very closely related to a subalgebra in omega. And yes, you might need to redefine with using some scalars with those minus signs. You might need to opt something.
Good. Thank you, Josh, once again.
Thanks.
We